All right, class. I think this is where we left off last time with the fundamental theorem of invertible matrices, version 2. Throughout the class, we will continue as we learn more about matrices and have new ideas, we will update this. So now you have 10 things. I may have showed you all 10 of these before, but the book only had 5. So rank... If the rank of A is n, so this is for an n by s square, n by n matrix, then all the following are true or all of them are false. A is invertible. A is row equivalent to the n by n identity matrix. The equation ax equals 0 has only the trivial solution. Ax equals b has exactly one solution for each b in Rn. The rank of A is n. The nullity of A is 0. So the only point in the null space is, there's only one point in the null space, and that's the origin. The rows or columns of A are linearly independent. The rows or columns of A are span Rn, and the rows or columns of A are a basis for Rn. All of those are, if you get one of those, you have all of those. So, okay. So here's a statement of a theorem. So since a basis is a minimal spanning set, you might already have the idea that any point in the space could be represented by a linear combination of the basis vectors. Like since it spans, so of course it can, but since it's a minimal set, there's only one way to write any point in the subspace as a combination of basis vectors. That's what this theorem says. There's only one way. If we're trying to write x as a combination of these b's that's in our basis script b, then these combinations, these scalars, c1 to cn, they are unique. So there's only one. And we call those weights, we call these c's, we call them coordinates. And you might think, but x already has a set of coordinates. It has like if I told you, hey, what combinations of b do you need to get to x? And let's just say we're working in R3 here, and I said x is 1, 0, 3. And so you're like, okay, well, it's already got coordinates, 1, 0, 3. It does have coordinates. These are the coordinates relative to the standard basis. That's the standard basis, and those would be 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the standard basis, and this coordinate of 1, 0, 3 means 1 of these, 0 of these, 3 of these. So, but it has another coordinates. If we pick a different base, if we pick those bases or the building blocks and kind of the directions that we go, then it's going to have a different set of coordinates for those things. So the coordinates of x relative to the basis b, or the b coordinates, script b coordinates of x, and this is the notation we use. So we put the name of the vector in x. Sometimes we could write we usually put the name of the vector, and then here is the basis we're referring to, and then these are the coordinates. Okay, coordinates. I do not like the way that Adobe makes my handwriting even worse. So it's the coordinate vector of x in the basis b. So we'll talk more about this. I'm not going to prove this, but I am going to give you an example to try to way to think about what's going on. So it's going to be a food example again. And I'm going to jump over to this screen here. So if I'm dealing with protein, fat, and carbs, okay, this is peanut butter, bread, and jam. Each of the columns is a pivot column. This is a linearly independent set. So it forms a basis for protein, fat, and carbs. So one way of thinking about coordinates is I can think about my dietary goals as protein, fat, or carbs, or if peanut butter, bread, and jam make up a basis, I can just think about it as peanut butter, bread, and jam. You can tell me either one, as long as you tell me which world you're living in, and that still has all the same information. I can tell you, so this over here in this yellow, this 90, 60, 260, this is about the daily intake I should have in terms of protein, fat, and carbs. So I could say, hey, my dietary goal is 90, 60, 260 in protein, fat, and carb basis. But I could also say, hey, my daily goal is 3, 17, 8 in peanut butter, bread, and jam basis. Those have the same information. You're saying to yourself, why in the world would you do peanut butter, bread, and jam? Protein, fat, and carbs is so easy, right? It is. This is the standard basis for protein, fat, and carbs. We'll attack that later because it turns out there are some bases that are even better than the standard basis when dealing with matrices and when dealing with some contexts. So, but these are both equally good. This is the matrix that connects the two. This is actually the inverse matrix. It's rounded to 1/10. So I actually found 3, 17, and 8 by multiplying this inverse matrix by the 90, 60, 260. But I could also pick another basis. This is milk, oatmeal, and sugar. And this is the matrix that connects it to protein, fat, and carbs. And this is the amount I need to eat every day. Or that doesn't make much sense. This is really heavy in the carbs, and I need to cut out 200 servings of sugar a day. So I could tell you, hey, I need 90, 60, 260 in protein, fat, and carbs. I need a negative 3473 or a negative 1 and a negative 198 in milk, oatmeal, and sugar. Or I need 3, 17, and 8 in peanut butter, bread, and jam. All those are equivalent. Those are all coordinates of my dietary goal, just in different coordinate systems, just in different bases. So that's the idea, is you can tell me a basis. It doesn't have to be the standard basis, and I can tell you the coordinates. So just to be clear, like this 3 tells me how many peanut butters I need, and then this 17 tells me how many breads I need, and this 8 tells me how many jams I need. And if I multiply this by this matrix here by 3, 17, 8, I'll get 90, 60, 260. So, and if I multiply 90, 60, 260 by the inverse matrix, I'll get 3, 17, 8. Okay, so that was the idea on that one. Here's a visual interpretation. So here's the standard basis. You can think about this. You can think about it as x, and this is y. So getting to v, we would think about that as, oh, that's 1, 2. Yeah, it is in the standard basis. So script e here, that is the coordinate in the standard basis. But if we're not using a standard basis, we're using something different like b1 and b2, I can still get to v. That's the same spot. But the coordinates here are a -1 and 2. I go a minus b1 and I go 2 b2s. It still ends up being at the same spot. You can convince yourself if you pick b2 to be, I think it's 1, 1, and b1 to be 1, 0. So a -1 b1 plus 2 b2 gets you, it gets you to the same spot. These are the coordinates. That's not the spot it gets you. These are the coordinates in this basis, script b, to get to the same spot. So you can say, where are you at? Well, I'm at 1, 2 with the standard basis, or I'm at -1, 2 with the script b basis. So I've already talked a bit about the standard basis, so script E usually is what we pick to be the standard basis. We have E1 to En. Denote the standard basis for Rn for the vectors. For this vector, find the coordinate vector of x relative to E. Well, this is the easiest one because that's just a -1 times E1, like this 1, 0, 0, 0. It's 3 times this. It's 5 times that, and 0 times that. So I did set this up. These are two different ways to set this up. But either way, like the only way to get 3 here is I have to have this one multiplied by something, and that something's only C2. So C2 has to equal 3. All the other terms are 0 in that row. So C2 has to equal 3, C3 has to equal 5, C4 has to equal 0. So like this is the coordinate system you're already used to thinking about. Okay, here's a new basis for R3. So these are three linearly independent vectors. Let VB be 3, 2, 1 in this basis. Then find B. This should say find B in the standard basis, not just V. Find V, the coordinates of V in the standard basis. So this is easy. I can just take 3, 1, 0, 1 plus 2, 1, 1, 0 plus 1, minus 1, 0, 1. And that is, I'm going to have 3 plus 2, so that's going to be 5 minus 1, so I'm going to get 4. I'm going to have 0 plus 2 plus 0. Then I'm going to have 3 plus 0 plus 1, so that's 4. So 4, 2, 4. And you might be thinking, but that's exactly matrix multiplication, and that's right. This times 4, 2, 4, oops, times 3, 2, 1. Oh, it does not like 3s. 3, 2, 1 equals 4, 2, 4. So you can think about matrix multiplication by if you have a square matrix that's invertible, you can think about it as a way to change bases between, a way to change coordinates, or finding new coordinates in a different basis system. So that'll come to be important, much more important later. So, okay, so here's going the other way around. So here they gave us 3, 2, 1. They gave us this one. We just had to find out what it was, the other one. Well, now it's the other way around. They're going to give us x, and we have to find out what the coordinates are with respect to b. So they're going to give us, they're giving us this one, but we have to find that. So, but this still should look familiar on how to do this. Really, if we write these down as a matrix, over here on the left, we can write it down as a matrix times the coordinates we're looking for, and that has to equal to 0 and a -3. And that's just solving a system of equations. And I row reduced, and I got this. So C1 has to be a -1/2. C2 is 0. C3 is a -5/2. And so the coordinates of x with respect to b are that. And you can check, and if you take a -1/2 times b1 plus 0 times b2 plus a -5/2 times b3, you will get x here. So, and that's it. That's coordinates. So it's really a different way of thinking about what we've been doing already about solving systems of equations, but it really refers to solving systems of equations where you're dealing with an invertible matrix, because no information is lost. You can go back and forth, and you can write the coordinates with respect to one basis or another basis, and you can go back and forth between those. You can have your protein, fat, carbs, or you can have your peanut butter, bread, and jam, or you can have your milk, oatmeal, sugar, whatever basis you want. You can pick it, and then you can write your goal in that basis, or any vector in that basis. So hope that helps. Shorter video today.